Hey friends, here we go again. We are going to now look at the electron configuration. I happen to love electron configuration. Pretty sure you guys have done a very basic of this before, but I want to go over everything with you so that if it's a review, it's okay, and if it's brand new, it's okay. So first off, with the electron configuration, the whole point of electron configuration is we need to have an idea as to where electrons are in the atom so we know what those electrons are doing. And so we also know how to manipulate those electrons so we can make compounds so that we can predict to see what's going to happen when we mix something. So electron configuration can be really, really important. We use a symbol that contains 3 pieces of information. This is really important, and you probably want to write this part down. So N is the number of the principal quantum shell. This actually is very similar to the periods on our periodic table. It's not perfect, but it lines up pretty well with the periods on the periodic table. The second thing is L, the letter designates the orbital type. What we're talking about here with the orbital type is S, P, D, and F orbitals. So we have half an idea of what kind of orbitals those electrons are like just hanging out in. Finally, the superscript number. Remember, superscript means above, so the number's like above. Designate the number of electrons in that subshell. So for example, if we come down here and we look at this piece for electron configuration, we have this 2, and that's the number of the principal quantum shell. We have the P, and that tells us the orbital type. And then the 4 tells us how many electrons are in that particular orbital. Now there's something called the off-ball process. And the way that I remember this off-ball kind of makes me remember the term oddball. And we want to make sure that when we fill in our electron orbitals, we're not going to be oddball. And so we got to make sure we got to stick with the off-ball process, meaning that we're going to fill the lowest energy levels first. Notice here, we have a chart with increasing energy. So S's have the lowest energy, then P's, D's, and F's. So we fill, if you not follow these arrows, we're going to fill the 1s orbital first, and then the 2s orbital, and then the 2p, and then the 3s, and then the 3p, and the 4s. Then this right here, you'll find this very useful later because you're going to go to 4s, and then you're going to want to say 4d, but you have to fill the 3d orbital in first, and it's because of the off-ball process. The 3D has less energy than the 4P, but greater energy than the 4S. And again, the off-ball process is we actually fill lower energy orbitals first. Sorry, my writing's not amazing on here, but it's okay. So we fill lower orbital energy levels first, and then work our way up to higher energy levels. Now, the filling rules for electron orbitals. We have 3 rules. First one, again, is the off-ball principle. That's where the electrons are added one at a time to the lowest energy levels available until all the electrons have been accounted for. Then we have this good old Pauli exclusion principle. What this says is an orbital can hold a maximum of 2 electrons. But in order to occupy the same orbital, 2 electrons must spin in opposite directions. So oftentimes when we write anything with the Pauli exclusion principle, we'll write arrows going up and down or half arrows going up and down to indicate that there are, in fact, 2 electrons in that particular orbital. However, they're going to spin in opposite directions because electrons, remember, like charges repel and opposites attract. Finally, we have good old Hund's rule. Hund's rule says electrons occupy equal energy orbitals, so a maximum number of unpaired electrons results. Okay, so Hund's rule comes from, let's say we have a p orbital, and we know that there's 3 lobes for a p orbital. And let's say we're going to fill our first lobe Then we have to put an electron in each lobe before we can go back and fill a second lobe, or a second electron in each lobe. The way that I remember this is when I was a kid, my mom called everyone hun. And my friends, everybody. And so I lived in a small town. And so people would come and just play at my house. And basically, whatever house we were at when it was time for lunch, that mama made peanut butter and jelly sandwiches or ham sandwiches or whatever was on hand, grilled cheese, whatever. So we all just ate at wherever's house we were at that particular day. So it happened at my mama's house a lot. And so again, just looking at this, the way that I remember this is mama feeds all her huns first before anyone gets seconds. So everybody got a peanut butter and jelly sandwich first before anybody got seconds. So that's how we fill in electron orbitals. Now, the orbitals that are actually being filled, we can look at this kind of like the periodic table. So you'll notice this section again here. This section of 2 columns, this is our S block. This section of 6 columns, this is our P block. Our middle section, our transition metals, is our D block. And our inner transition metals is our F block. And you're going to start to see why the periodic table is so important to understand and how to use. You can see the colors on there to indicate your S, P, D, and F. One thing I want you to notice is that helium over here, helium is actually part of the S block. So we're going to pretend it's kind of in this spot right here whenever we do electron configuration. Now, when we align electrons with the configuration, what we'll do is we have one S, and again, that helium we're going to pretend is an S orbital. 2S, notice what we're going to do is basically follow our periods. 1, 2, 3, 4, 5, 6, 7. Okay? What I want you to notice, though, is on the periodic table, as we look across, we see 3S, 3P, 4S, 3D. This goes from 4S to 3D because of that good old Aufbau principle. So go back to the Aufbau principle to help you understand why it goes from 4S to 3D. 4S has lower energy than 3D, therefore we have to fill the lower energy levels first before we go on to fill the upper energy levels. Now, the Pauli exclusion principle tells us that electrons in the same orbital have opposite spins. So here we have our 1s orbital, and that basically we draw it. Notice it's drawn with one box, because if you remember, an s orbital is a spherical shape, and there's 2 electrons hanging around in that spherical shape. So of these 2 electrons, this indicates one electron, this indicates a second electron. But this particular rule tells us that the electrons have to spin in opposite directions. And again, it's because like charges repel. So just remember that. You know that from like playing with magnets when you were a kid. Or now, I still play with magnets. Okay, here's an example of Hund's rule where mama feeds all of her Huns first before anyone gets seconds. So of course, when we go to do electron configuration, we're going to fill our 1s orbital first, then we'll fill our 2s orbital, and notice what happens on the 2p. We put 1 electron in every lobe first until we fill a second electron in all the lobes. So mama fed all of her Huns before anyone got seconds. Same thing with the 3p. We fill all of our lobes first before any of them get seconds. So we have something here that can really help us with electron configuration, and we call them box orbital diagrams. Oftentimes, I'll just refer to them as orbital diagrams. Sometimes I forget the term box, and a lot of people do as well. So if I want an orbital diagram, you're going to have to draw it in this fashion, where you're going to indicate an s orbital has 1 lobe and can hold a maximum of 2 electrons. A p orbital has 3 lobes. Each lobe can hold 2 electrons. for a total of 6 electrons. An s orbital, 1 lobe, a p orbital, 3 lobes for a total of 6. So what happens here is we have hydrogen. Here's our orbital box diagram for hydrogen. We put 1 electron in a 1s orbital. For helium, we have 2 electrons total. So our first s orbital is going to have 2 electrons for that. Lithium, we have 3 electrons. Boron, notice we have 5 electrons. So we're going to fill the 1s, fill the 2s, and then there's 1 electron going to be in the 2p. Nitrogen, we have 7 electrons. We'll fill the 1s, fill the 2s, do the Hund's rule. For chlorine, we have a lot more electrons. Notice we have Hund's rule with 2p, and we fill our 3s. Now notice we have Hund's rule again with 3p. So the orbital type, the way the orbital filling diagrams, again, this would be the orbital box diagram right here, where this is going to be our electron configuration. So I'm going to show you in a minute how to use the periodic table to figure out the electron configuration, and it's really beautiful how it works. There are some exceptions, and we're going to go through this in class together, and we will figure all those out. But I want you to look at these box orbitals now, and then I'm going to do another little demo using the periodic table to find electron configuration.